To study the dependency of the photoelectric effect on the various factors, an experimental setup is made and shown in the figure. In the figure, there are the two electrodes. One is the cathode, which is kept at the negative potential, and this is the source of the photoelectrons. Another electrode is anode, which is kept at the positive potential, and it collects the electrons. As the electrons complete the circuit after reaching from cathode to anode and then through the battery again at the cathode, a current is constituted, which is the photocurrent, and this current is measured by the emitter. The electrons emits from the cathode or the emitter because of the incident radiation. This is the photoelectric effect, and this radiation has a particular frequency, say nu. So this experimental setup helps us to study the dependence of photoelectric effect on the intensity of the incident radiation, potential difference V applied between the emitter and collector, that is the cathode and anode, and third factor is the frequency of the incident radiation. First is effect of intensity of incident radiation. Here we draw the graph between the intensity of the incident radiation and the photocurrent. This graph is the inclined straight line. It states that as the intensity of the incident radiation is increased, photocurrent also increases, because intensity refers the number of photons falling on material surface per unit area per second. Therefore, if number of the photons falls on the metal surface increases, that results into the number of photoelectrons emitted from the metal surface and constitutes the higher photocurrent. Here we have to note that this emission take place for the frequency greater than the threshold frequency. That means if frequency is less than the threshold frequency, photo emission will not take place. In that case, there will be no current. This graph is obtained when frequency is greater than the threshold frequency. Second is effect of potential. If we draw the graph between the photocurrent and the potential applied between the emitter and the collector, if we use the photocurrent on the y-axis and the potential V on the x-axis and draw the graph, then the graph will be like this. As per the graph, if the frequency is greater than the threshold frequency, then using the Einstein photoelectric effect, h nu equal to, that is the energy of the incident photon, work function, that is h nu naught, it is the work function, plus kinetic energy max, maximum kinetic energy. And this kinetic energy, which is the energy of the emitted electrons, is equal to the charge on the electron multiplied by the stopping potential. This is the potential which is required to screen the electron from reaching the anode. Therefore, if the frequency of the incident photon is greater than the threshold frequency, then if applied voltage is 0, this is the V equal to 0 between the collector and the emitter, then some of the electrons have the so much kinetic energy that they reach the collector. as we increase the potential V, more and more electrons have a tendency to reach the collector and increase the photocurrent. And after a sufficient voltage, all the photoelectrons emitted by the emitter reaches the collector and result into the maximum photocurrent I naught for a particular intensity, say I1. I1 is the intensity of the incident radiations, that means number of the photons falling per unit area in per second. In this graph, if we check, there are some current if we applied the negative voltage. This negative voltage refers that it repels the emitting electron and try to oppose to reach the collector. And at a particular voltage, say V naught, all the electrons are screened and they are unable to reach the collector. So there is no photocurrent, that means photocurrent becomes zero, and this potential is called stopping potential. Now for the same metal surface, if we applied the increase the intensity of the incident radiation, the graph will be like this. This has the intensity I2. Here this I2 is greater than I1. Here more number of the photons are falling per unit area per second on the metal surface. So more photoelectrons are emitted and they constitutes the more photo current. But because the stopping potential is the property of the material surface, so these two graphs have the same negative V naught, that is the same stopping potential. Similarly, if we further increase the intensity, then graph will be like this third graph, I3 having the intensity I3, and the relation will be I3 is greater than I2 is greater than I1. Again here stopping potential is same because the metal surface is same. It is independent of the incident radiation intensity. We can also draw the stopping potential graph versus frequency using the Einstein equation, and this is the h nu equal to h nu naught plus k max, and this k max is equal to the E into stopping potential. This implies that EV naught equal to h nu minus h nu 0, or we can write V naught equal to h by E into nu minus h nu 0 by E. If we check this equation, this is the equation of a straight line. If we consider or compare this equation with the equation of a straight line, it is just like phi equal to mx plus c. So the m is the slope. So slope of the graph is h by e. That means slope of the graph v naught versus nu remains constant because slope is h by e, which is a constant. And this negative minus h nu by e, this is the intercept on the y-axis. That is, here it is the stopping potential axis. So now we draw a graph. On x-axis we represent nu, frequency of the incident radiation, and V naught is the applied stopping potential which opposes the motion of the photoelectrons from cathode to anode. And the graph is like this. This is a straight line. This graph has the slope tan theta equal to h by e. This is a constant. And the intercept on the y-axis is minus h nu naught by e. The stopping potential is 0 the frequency is called nu naught. This is the threshold frequency. This frequency refers that if frequency is greater than nu naught, then only the photoelectrons are emitted. If frequency is less than nu naught, there will be no emission of photoelectrons, so no photocurrent. Suppose we have to draw the graph for the another material which has the threshold frequency say nu naught 2, and this nu naught 2 is greater than nu naught. Therefore, this nu naught 2 will be here because it is greater than the nu naught, and the graph will be like this. And here the intercept will be minus h nu naught 2 by E. And both the graph have the same slope, that is equal to h by E. Third is effect of frequency nu of incident radiation. If we draw a graph between the photocurrent I and the collector voltage V, let the I is the intensity of incident radiation and nu is greater than nu naught, that's the threshold frequency. So graph will be of the shape as shown in the figure. As per the figure, when frequency is greater than nu naught, that is frequency is more than the threshold frequency, then it emits the photoelectrons, and some of the photoelectrons have the ability to reach the collector without applying the collector voltage. And as we increase the collector voltage, the number of the electrons emitted from the emitter reaches at the collector and increases the photocurrent. And a particular voltage, all the photoelectrons emitted from the emitter reaches the collector and the photocurrent becomes constant, say I naught. It is the maximum photocurrent. If we applied the negative voltage, some of the electron which were reaching the collector decreases and the photocurrent decreases, and in a particular voltage, this is called the stopping voltage, which is a negative voltage applied at the collector, causes the photocurrent to be zero. That means none of the photoelectron is able to reach the collector. For the same intensity, if the frequency of the incident radiation is increased, suppose this is the graph for the frequency nu 1. Now we increase the frequency. In that case, an intensity is the same. For the same intensity, this maximum current will be same. Einstein photoelectric equation is h nu, that is equal to h nu naught plus k max. Here h nu is the energy of the photon incident on the metal surface. H nu naught is the work function of the metal surface, and kinetic energy is the maximum energy of the emitted photoelectron. As we increase the frequency, then the energy of the photon increases and work function of the metal remains same. It is same for the same metal. On increasing the frequency, the kinetic energy also increases. If kinetic energy increases, then the stopping potential required to stop these photoelectrons to reach the collector also increases. Therefore, if we draw the graph for the higher frequency, then graph will be like this. This is the stopping potential, say minus V naught 2 for the frequency nu 2. and first graph is the frequency nu 1, and intensity of the radiation is I for the both case, so the maximum photocurrent will be same. Hence in the graph the frequency nu 2 is greater than nu 1.